Hello,
Oh,
how are you?
much better.
Good, good. So, hello, Pakhi and Morgan and Dick. I don't know if you had any updates before we get started.
Hey, hi. I do have an update.
Okay.
I'll just back 1 second.
So I got extensions for both Pakhi and Mahul for their projects. So now they're due 3 weeks later or 4 weeks later. I can't remember what the date was that I confirmed. I sent a message to both Pakhi and Mahul about it. So whatever that date is the correct date for submissions. I think it's like about a month late or a month extended. And so now, I expect that everyone be on time with that. And then that brings me to this idea of a stopping point. So, you can continue a project forever, I suppose, and keep adding things in. And we don't want to do that. We want to that's one of the reasons why they have a deadline. So you find a good stopping point where you can say, okay, that's enough work for this thing, this unit. And then I'm going to take it and I'm going to kind of wrap things up and then maybe create issues for later work. So, we might say, okay, I've got this thing built. Now I'm going to maybe test it a little bit and then write up some documentation. And then maybe later I can do some, additional work on it, add some features, that sort of thing. So we want to have a good stopping point. And I think, it's just a matter of thinking about how you want to present this to as your final submission. What do you think will be a good package? What will work as a single unit? So remember, you're handing in this project where you have code, you have documentation, it does something, and you can demonstrate it. And maybe not everything that you're working towards is completed, but it's good enough so that you can submit it and feel good about it, and then say for the future we're going to add in more features, and that's really what they want. So we will talk about this more as we get closer to the deadline, but just to let you know that that's the kind of the way you have to think about it. You can't just, I don't want people to feel like they have to build this super complete thing. You can always find a stopping point and kind of get to that point, and that's what you need. So that's okay. So that's good. Hello, Susan.
Hi.
Hi. So so Pakhi, you wanted to give your update.
Yeah, hi.
Hi.
So I'll just share my screen.
Okay.
1 second. Okay. Yeah, so I added the data set to the code that I was working on, and this is what the growing graph now looks like. So as you can see, there's this node which does not have a label yet. So I need to recheck why that is happening. I believe this is the P0th lineage, P1, from P0 we have one P1 cell, right? I think it's that one, and it's not able to divide that one specifically, so I just need to check that. And I also added the vector embeddings and the coordinate positions as the embeddings. So but I just need to make a few more changes to back propagate the distance, the Euclidean distance losses and all. So I will be working on that today and tomorrow. I think it's almost complete. After that, the graph will be able to learn and train on its own. I mean, it's not perfect. The growth might not be very accurate because the data set the data set is only for just one embryo, right? And that too, I was looking at the the last values of the division in the CSV file. I think it's the other one. So over there as well, I think some cells, the data is missing in some cells. So I was thinking of like not generating it to like all the 900 cells that it will have in the end, because that part might not be very accurate, but like stop it somewhere before that to have like sort of an idea, so that like the model doesn't learn some irrelevant stuff basically. So that's what I was planning right now. But yeah, like I was able to like train it according to the data that we have now. And I just need to check this P0 thing and just the Euclidean distance that I was mentioning. So yeah, I think this should almost be done like in a few days, like 2 to 3 days. In my proposal, I had mentioned that I would be implementing the K-mapper algorithm along with this, because then like at one point the graph would be too large to understand anything. So there I wanted to implement the algorithm to make it like more informative and all it, and visually a bit clear. So that's why I like requested for an extension to like include that feature as well, because I'm not sure like how much time that would take, because I'll have to put it in like different stages of growth. So yeah, that's what I wanted to mention. And I figured out why the environment was not working in the DevoGraph repository as well. So I think I'll fix that and be able to push that in a few days as well. So yeah, this was my update. Am I audible?
Yeah, yeah. Yeah,
Oh,
thank you. Yeah. So yeah, it looks good. Looks like you've got, so you said that you had some problem with one cell dividing. Was it P0 or what was the?
yeah. Like after P1, I think it's not able to like gather information about it. I think according to the division timings, I think that CSV file is somewhere else. Yeah. Yeah, like this P1 cell, like it will like divide into EMS and P2 cells. It is not able to recognize that for some reason. So I just need to check that. But for AB, it's working fine as of now.
Huh. Okay.
Yeah.
Well, yeah. I don't know what I don't know what to say about that, but
Yeah, I think it's something with the code only. So I'll just check that. Like,
okay.
yeah.
Sounds good.
Okay.
Yeah. So that's
Yeah.
great. Yeah. Thanks for the update. Yeah. It looks like you're coming along on it, solving problems that are arising, and then yeah, making the graphs more interpretable is good, and just kind of working on that. That's so we'll maybe I think that's worth the extension. We'll talk about that though as we get along, and then I hope to see your push. I guess later this week.
Yeah, I'll make that.
Okay, that's
Sorry about
good.
that.
Yeah,
Also, one more thing. I think I'll have to leave early today
it's okay.
because I have to go somewhere. So I'll just like leave now if there's no more questions about the update.
We don't have any more questions, so okay. Thank you.
All right. Thank
All
you
right.
so much.
Thank you. Bye. All right. So Susan, I don't know if you had any updates from last week.
Just attended CompuCell3D, and it's a mosaic model. And I guess I found out the reason why there's no exact forces stated in a lot of these papers, because they just do a force that approximates a force that attaches one cell to another cell, or that will do cell sorting. So they adjust the surface tension so one cell will fit inside another cell, or you can call this blob a nucleus and put it inside another cell. It's so it's sort of an approximate force. So they said, well, you try it out in CompuCell3D, and then if you want to get more elaborate or more exact, you use Tissue Forge.
Oh, okay.
or for more exact measurements. So that's because it takes longer to set up in Tissue Forge.
Right.
And it's great to try out ideas in CompuCell3D. However, I'm dealing with engineers. I get to do hardcore, how many nanonewtons is that exactly? Or my paper's worthless? Like I can't do, oh, well, it's sort of like the force. No.
You know, like they frown upon that. Yeah.
Yeah. So it was interesting, and I really wanted to do more, but just not going to work for my project.
Oh yeah.
Anyway, it's a mosaic model, and they definitely can do tissue sorting. They've got models for that, and then they've got a model for making a cell that moves, and you can kind of put a vector force on it, and it'll go in the direction you want it to go in, and then it'll divide. It's quite elaborate.
Yeah.
No precise forces.
Yeah.
Anyway, it explains the papers, and I'm going, where are the nanonewtons? And there are none. Yeah. So I guess that's the long and short of that one.
Yeah.
It's interesting, but I can't use it, so I'm going to have to not think about it until I'm finished. If I ever think about it again, I don't know. They were interested in the tensegrity that I was doing.
Well, that's good.
Told them a little bit about it. Yeah.
Have they done anything like that, like in another tissue type or organism?
They've wanted to incorporate something like a tensegrity into their model. They like to incorporate other things into their models, including the vertex model is a part of CompuCell3D. But I don't know how you'd put a tensegrity into that. Like it's a 3D tensional structure, and you put a force on it and it changes shape. So I'm not sure how they do that realistically.
Yeah.
Their Tissue Forge might be able to do that, because they're working with fibers.
Oh, okay.
Using that model.
Oh, I see. Because the cells are just kind of like these blobs. They don't have any discrete structures within them, so they.
No, they don't really have a discrete structure, and although you can kind of make them have one, like I said, using the cell sorting idea with different surface tensions.
Right.
And you can put a force from one blob to the other, but you can't say precisely what force, and maybe I'm doing them a disservice here because I wasn't paying that much attention because I had a bunch of other things going on, unfortunately. But yeah, it's just sort of, oh, well, we're going to make an epithelial tissue, and there's a basement layer, and it has a different surface tension, so it tends to hold together. And then there's the bottom of the cell, and then there's the middle of the cell and the top of the cell, and they all have different surface tensions, and then they need to stay apart in compartments. And then you can put a line at the top saying, oh, well, there's an attachment there. So I maybe should try modeling it to say how close to an actual cell you can get with it. I wanted to try, but like I say, things interfered.
Well, that sounds interesting.
Yeah, it's worth a look.
Yeah, it is.
They've got so many models that people use, and you can put a chemical gradient in them. And like I was thinking for epithelial cells, what you need is actin, myosin, calcium, and then ATP, and then you get movement.
Yeah.
If you could do something like that, when it runs out of the calcium, then it quits moving. Like you could do that.
Yeah.
With it quits contracting. But they were interested in doing the model where you contract one cell and then see how its neighbors react. They thought it was a good project.
Yeah.
So you should try it.
Yeah. Well, that sounds great. Thanks for the update.
Okay.
And I don't know, maybe we'll have another person interested in working on that. Trying to experiment with it, and something beyond what you have time for.
Yeah, well, I had one person interested in it, but they just had that week, and then they're going to be doing a PhD, and I went, okay.
Yeah, good luck with that.
Good luck with the PhD. Anyway.
Yeah. Well. All right. Well, thanks. Yeah, that was a good update. We had last week. We had more detailed discussion about CompuCell3D and the workshop, and so that's all online. Those materials, and then some of the more focused things we want to do in this group. We had some discussion about that, and that's something that like I said, I was interested in that a long time ago, but I never found a way to really incorporate it in what we were doing. So it'd be nice to revisit that and get some bottles running and see what we can do.
Okay.
Yeah.
Yeah, that's a later date project.
Yeah. Hi, Hussain. How are you?
Well, it's a good Monday.
Yeah.
I love Mondays.
Yeah. Did you have any updates or?
Yeah. So cool. So I'm back from my quasi vacation. I guess ain't no rest for the weary, as they say. Always working. So okay. So I've gone through the for me to use TOPAS or to be part of the TOPAS Guild for community, I had to go through this introductory training workshop thing, and that's basically just backing up for a second. This is part of the breast cancer therapeutic bioRxiv project I've been working on Zeradic, as well as I posted about it in the Slack channel for this in the oral workplace. As I've been talking about for the past several months. And we're using TOPAS. TOPAS is a tool for particle simulation for modeling external particle therapy treatments. So for CT images, for SCORDAs, for fluids, things like that too. And I went through the training workshop to be part of the community, so we can make sure everything's on the same page. Right now, it's all about really reading through the documentation very, very thoroughly and making sure. And reading through the documentation very, very thoroughly. And that basically is what it is. A lot of it is really reviewing some of the fundamental physics involved too, like the physics and the chemical physics, like the geometry and the models for the algorithms, and getting a prototype. So getting a prototype specifically for some of the geometry that Dick and I have been discussing with the emails, as well as not just through Dick and I, but not just through me and Dick, but through everyone else involved. Like it looks like we've been talking with some other people that I don't know, like Lei Peng, Chen Xian, Shruti. Shruti's been here before, has she?
Yeah.
Shruti Bunch, yeah. Cool. So she's done some of the programming for some of the other algorithms too, and we had outlined some steps. I can briefly copy paste it from the email that Dick had sent into the chat.
Okay.
Excuse me, to the chat. So, what's it's private? You guys said it's private. Did you all see this in the chat?
Yeah. Yeah.
Okay. I was making sure. Because I thought I said the private, but yeah. Okay. Cool. So yeah, the breast cancer tumor podcast. You know, we definitely want to start with very simple prototypes, like on very simple squares, and then on 2 dimensions, like with an angle range from -45 to 45. And with very specific, as you can see, very specific, you know, technical details right there. So at this point, really, I just need to produce the results. Excuse me. At this point, I really need to perform the simulations using TOPAS and use TOPAS. The documentation is it's a bit cumbersome, but I'm trying to break my way through it. So.
All right. Okay. Yeah, that's good.
That's basically it.
Okay, that's all your update. Okay. Yeah, thank you, Hussain. That was so if you want to read, I'll read in the chat what you posted so people if you can't read it. So the RBRCT algorithm, perhaps MARTI with MARTI, an ML inpainting algorithm. So this is all for this breast cancer physics research. We're doing the inpainting. You're doing physics, and you're trying to do this physics simulation. So the inpainting algorithm, perhaps a step where all end lines are modified by the inpainting. So, Dick has been trying to develop an inpainting algorithm, and, maybe some of these stock algorithms might be helpful there. So like RBRCT and MARTI. And then contrast enhancement, perhaps by this fuzzy method, or prior chemical enhancement, or X-ray diffraction CT, or dual energy CT, just kind of a combination of things. Deconvolution due to a narrow angle range, detection of possible tumors, perhaps by template matching. If a tumor is detected, stop and ablate it. If the maximum dose has been reached, stop. So it's like some sort of search algorithm where you're searching this detection, if this detection step. If tumor is uncertain in X-ray, n+1 is okay, yeah.
Yeah, I think one word got cut off.
Okay, yeah. So yeah, that's great. So
I think the chat in the
yeah, reached its limit. It's okay.
Yeah.
Hello, everyone. Sorry to interrupt. Something's come up and I have to leave. So.
Okay, that's okay. Thanks.
Bye.
Bye. All right. So yeah, it looks like good work, and you're making good progress. You're learning about this new package that you're trying to use for this. I know you've been trying to find the optimal package.
Yeah, it's pretty straightforward. Like TOPAS uses what's called a PCS, parameter control system. So all the aspects of the simulation are controlled through text-based input files. Basically, as long as you just download it, you'll have like a specific text file. You just edit whatever you specifically want to do, and you shoot off it for the simulations. It performs simulations for you. And once it gets built on the key to a bit. So Dion for like simulating particles in different manner and stuff too. Excuse me. So yeah, really excited to keep in touch regarding like book chapters and other papers that we've been getting together. So yeah, whatever. Just really just really getting back into things. So.
Yeah, I think the original goal was to have a series of papers in this book, and so working out the problems for the paper, of course, but then also for just the technique itself, which might lead to some other things. So
Now, Bradley, can I?
Yeah, go ahead.
I can sort of simplify it. Most pictures are taken by a single snapshot. Okay, and that means you predetermine that there's enough light. You might use a flash or something, and then you get one picture. The general procedure here is that we take a picture with a small amount of light, in this case X-rays, and we make it as good as we can. That's what the purpose of the in-painting is. And then we see if it's good enough to detect a tumor.
Okay.
If it is, we're done. If we're not, we add some more dose. So you get to take a repeated picture with more and more dose until you have a stopping point. Okay, so that's the general method then is shoot with a certain amount of dose and then see what you got. And then if it's not good enough, shoot with some more.
Yeah.
Okay.
Yeah.
So in a sense, it's a very general approach to imaging, which as far as I know has not been used. The only thing that would be similar I can think is the human experience of dark adaptation, where you get more and more sensitive to the dark the longer you're in it.
Oh yeah.
For about half an hour.
Yeah.
Okay. So it's a strange way. It means you have to do it's image dependent addition of dose. So every step along the way is image dependent.
All right.
Okay.
Yeah.
So that's the way of simplifying all this. It's shoot, look, not good enough, shoot some more.
That's good.
Okay.
Yeah. Yeah. That sounds good.
Yeah, especially automating this, using machine learning and then AI. For sure.
Yeah, we want to use this.
Those approaches, like once again, really excited. Jake, perhaps you could just clarify who is on board for this project, because I did receive quite a few emails from
I don't know. Let's see who shows up.
Okay. I'm just curious because you did mention some people we've not discussed.
Oh yeah, okay. They have volunteered at different degrees or timings and whatnot. We need to see who's serious enough to get into it.
Excuse me.
We're holding a meeting on SM. What's the name of that channel? SM something.
For what?
Yes, my room.
Yeah. That's this is DevoWorm.
SM room.
Yeah, that's the one. The other one.
If anyone wants to join in.
Okay. All right.
Okay.
All right. Yeah, that's good.
That's the link to the SMN room.
Okay. Yeah. Okay. Good.
I think it auto changes the URL whenever you put it in there. So.
Oh yeah.
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 All right. Yeah. So, by the way, I'm really taken aback by how versatile, how broad TOPAS is, and it does seem really easy to use. I thought it'd be some really clunky, cumbersome, like trash built by an academic who doesn't know software. But no, it's actually pretty decently and well put together and stuff. So, yeah.
Good. Yeah.
Cool.
Yeah. What is the link to the software?
I can show the link to TOPAS.
Yeah.
So this is
What's the name of it? Type it in.
TOPAS.
Yeah, this one.
TOPAS. You have to forgive me. I live in a household where my family is from many different places, and all pronunciations all say splash all the time. So I've always been
So this is TOPAS here.
Oh, are you sharing screen?
Yeah.
Okay.
So this is a tool for particle simulation. This is it looks like it's an open source platform, and of course you can do extends the GNNs simulation toolkit to make advanced Monte Carlo simulation of all forms of radiotherapy easier to use. So this allows you to do things with microscopy images or CT images, and you can also do advanced physics simulations, 4-dimensional simulations, and I've never heard of a parameter control system. Maybe I'm
Yeah,
just
it's
like,
PCS.
yeah, PCS. Maybe I'm just not on the loop on that, but
Yep. I mean,
yeah,
it's it's like, what else can you ask for a scientist who doesn't, not speaking on my behalf, but any scientist who really needs to perform the research and get things done, but they can't afford to, get too nitty-gritty with, low-level languages or something
Yeah.
super complicated, and they're just like, what if I just give you a file of the, equations that I'm trying to solve, and it's like, yeah, it's perfect, it's perfect. So that's what makes TOPAS really, really useful and really good.
yeah.
I shared a few screenshots, by the way, in the Slack. You mind if I just share my screen for a second?
Yeah. Yeah, let me unshare mine. There we go.
Yeah. So yeah, there we go. So during the meeting last month, introductions to Javascript new user training. Which, by the way, I'm also glad that they make us go through these workshops and meetings, because that really helps us make sure that people who are using the software all at least have some sort of understanding of this. And but here's an example of a pencil beam or Monte Carlo, and examining the difference between the head and neck study based off of just 10 beams of different directions. So, really cool things you can do, and yeah, just what is that? So, yeah.
Great. Yeah, it looks pretty nice. And a pretty nice tool. And yeah, you went through some trainings on it, so you're kind of up to speed on it now.
Excuse me. Yeah. Yeah, I think that's basically all I had to share. So just headed to keeping up with everybody getting on board with this project, seeing where we can go with things.
Yeah, it's great. Well, thanks, Hussain and Dick, for the update on that. Looking forward to seeing it kind of come to fruition. It's good. Okay, yeah, Morgan. I don't know if you had anything to share. Looks like Susan's back. Let me share my screen. So yeah, well, let me get into some of the things I was going to talk about today. So again, this is our DevoGraph GitHub repository, and we've been talking about the different projects this summer, and so this is where, of course, everything's being pushed. So at the end of September, our projects will end, and this will be updated to reflect the projects. So Mehul's been pushing to hyper DevoGraph this directory, and I think Pakhi's been pushing to stage 2. So she's been working on some of these stages independently. So the goal here is to sort of get this maybe more organized, or maybe even put together a paper based on some of this stuff that's in the repository. And so, we've been working on this repository for 3 years now. We started with Jia Hong and Wataru and Longhe. I think Longhe was working on this as well 2 years ago. Then we had Sushmant last year. Himanshu was also working on it. And then we had this year Mehul and Pakhi. So we've got a number of developers working on DevoGraph. Now we need to kind of turn this into something, that approximates, sort of a first draft of what we've been doing and show it to the world. So that's going to be sort of a goal for finishing out the year and into the next year. So that's just an update on this project, DevoGraph. The next thing I wanted to point to was that last week we talked about sort of the physics of microorganisms and the microscale, and then going into the nanoscale. And Susan pointed out that in I think it was in CompuCell3D, they don't really account for the nanoscale effects of very small systems. So if you have living systems sort of at the boundary of the nanoscale effects, you see this in nanotechnology too, where you have nanoscale effects that are very different from microscale effects, and it's hard to model those in the same environment.
the tensegrity models I'm making are also not nanoscale.
Yeah, yeah.
Because they're there is a nanoscale modeling you can use in CompuCell, but it doesn't go into truss. The truss model is not connected to the nanoscale model, so I'm not sure their logic on that. You're supposed to be able to scale trusses, but that doesn't work.
Yeah.
Yeah. Yeah, it's starting to be harvest here very soon, and they're rushing around getting everything ready.
Yeah, yeah.
So I get, we need our truck.
Oh.
Yes, anyways.
Susan, I've got a question. Can these systems simulate stretch-activated contraction?
You could set up CompuCell3D so that it does.
Okay, because the propagation of differentiation waves and the contraction wave, we're speculating is stretch-activated contraction.
No, that would sounds like a good guess.
You know, when one cell contracts, it expands the neighboring cells, and they contract.
Yeah, well.
But that's just a qualitative guess.
Well, it just seems like it is, but oh well. One has to prove these things.
Yeah.
Yeah.
Obviously, there's a range over which it'll work, a range of parameters.
Yeah, it's CompuCell3D is a mosaic model, what they're calling a mosaic or a patch quilt type model, and it's sort of like the automata, so you can put rules into it.
Oh.
So yes, you could do that.
Okay.
Yeah. That's good.
So like I said, it's a very interesting program to mess around with. And if you don't want to get serious, you go to their Tissue Forge model.
Yeah.
Personally, I'm going to have to stick with hardcore finite element analysis, even if it doesn't quite work for tensegrities. So I'm not sure what sort of modeling would work with tensegrities properly.
Yeah. I don't know.
I'll be reviewing the math and I'll tell you about it later.
Yeah, yeah. So, yeah, we were talking about the differences of, different systems at different scales. So you have nanoscale effects that are different from, say, microscale effects. But you also have things going on at the microscale that are, very small scales that are different than, like, larger scales. And this brings me to this, talking about sort of a life at low Reynolds numbers. So this is a classic paper from 1976. This is by E.M. Purcell. This is called Life at Low Reynolds Numbers. And so a Reynolds number is a way to characterize turbulence and flows. And I'll talk about Reynolds numbers in a minute, but like this is basically a paper on considering life in this regime of a very low Reynolds number. So very briefly, a low Reynolds number represents sort of a laminar environment where there's no turbulence and things are very they're almost in stasis with respect to flow. So like, if you're in a liquid, the liquid is basically very laminar. It's, there's no flow, there's no turbulence at all. At a high Reynolds numbers, you have a lot of turbulence. So people use the Reynolds number in like fluid dynamics to characterize the flow. But what this paper argues is that there's this whole regime of life, very small organisms, single cell organisms that live in this regime. And so it affects the way they behave, the way they move, the way, even their evolutionary constraints. Because if you imagine like larger marine organisms, they're living at higher Reynolds numbers where they have to deal with turbulence and flows, and their bodies are sometimes adapted to turbulent conditions. And, so, there a lot of organisms at larger scales tend to be hydrodynamic and things like that. So this is kind of what this was based on a talk that was given on this regime. So this kind of goes through like the changes in viscosity in these different types of environments.
Just students.
So we have, okay, in this case, in figure 1, you see an object which is moving through a fluid with velocity v. It has a dimension a. In Stokes' law, the object is a sphere, so you just imagine an object as a sphere. But here it is anything. NNP are the viscosity and density of the fluid. The ratio of inertial forces, which is the resistance to the flow, and the viscous forces, as Osborne Reynolds pointed out slightly less than 100 years ago, is given by these set of equations, where V is called the kinematic viscosity. And so this kind of goes through the Reynolds number, and when this number is small, the viscous forces dominate. Now there is an easy way, which I didn't realize at first, to see who should be interested in small Reynolds numbers. So the viscous forces are sort of the opposite of turbulent forces, and that is if the fluid has certain properties, those are the forces that dominate the organism. So it's a very different set of conditions that the organism is in. And so this kind of talks about, in other words, if you want to tow a submarine with a Reynolds number 1, or strictly speaking, 1/6 pi, if it's a spherical submarine, tow it with 10 to the negative 4th DYN. So it's clear in this case you're interested in small Reynolds number if you're interested in small forces in an absolute sense. The only other people who are interested in low Reynolds number, although they usually don't have to invoke it, are the geophysicists. And he talks about the Earth's mantle having a viscosity of 10 to the 21st pascals. Now, if you work out this equation, the force is 10 to the 41 DYN. That is more than 10 to the 9th times the gravitational force that half of the Earth exerts over the other half. So the conclusion is, of course, that in the flow of the mantle of the Earth, the Reynolds number is very small indeed. So the idea is you're moving things through a liquid. If that liquid is dominated by viscous forces, it's very different than if you have turbulent forces. So this is, if you go back to this image here, this is figure 1. So this is figure 1 where you have this inertial forces over viscous forces, and he's considering the fluid density over the fluid viscosity. That's sort of the equivalence. You have A, which is this parameter here, so it's basically the size of the organism, this velocity, and then these environmental parameters out here. So basically, the organism is of a certain size. It's moving through this liquid. There's a certain viscosity here, and the environmental parameters determine how efficiently it can move through. So the shape, if you have a lot of turbulence, the shape has to be sort of hydrodynamic. If it's dominated by the viscous forces, it can be any size, or at least, but it can't be too big. This is showing a swimmer at a Reynolds number of 10 to the 4th. This is fishes at a Reynolds number of 10 to the 2nd. And this is a microorganism with a Reynolds number of 10 to the negative 4th, just to give you an idea of the scale and changes in the Reynolds number. And then this is, of course, some other equation. This is the Reynolds number represented in this way. So then of course down here you see this. This is a flagellar bacterium with a flagellum, and this just shows some of the calculations for that, where you have 3 to the 10 to the negative 5th. So that's the Reynolds number here, just showing like some of the calculations for very small organisms. And then this calculation for just kind of a theoretical calculation with respect to the Earth's mantle and the sort of the Reynolds numbers operating there, which are much, much smaller than 1. So just to give an example of where else you see those kind of Reynolds numbers. Then the Reynolds number article in Wikipedia. So this just kind of talks about how this is a dimensionless quantity that helps predict fluid flow patterns by measuring the ratio between inertial and viscous forces. So basically that's the ratio that you see in the figure here. And, for very small numbers where the viscous forces dominate, you get this different regime than the inertial forces where, or in cases where the inertial forces dominate. So this talks about, the difference between laminar and turbulent flows, or living in those kinds of regimes. So you can live in a laminar regime or you can live in a turbulent regime, but it's a very different type of life. And so this is kind of the lesson of this paper. So this is Purcell, Ian Purcell. So that's all I wanted to talk about with respect to kind of following up on that point. And I might also bring out some things on the difference between the nanoscale and the microscale next week. So I think that might be interesting as well to talk about. Okay, so the paper I wanted to talk about today was this paper on building a small brain with a simple stochastic generative model. So, there are a lot of small connectomes, and C. elegans, of course, has a tractable small connectome. C. elegans has a connectome with 302 neurons, and you have, a sizable, you can actually kind of figure out what the connectivity is of that, both synaptic connectivity and through gap junctions. And so we have those types of connectomes worked out. And we even know kind of how the developmental connectome works because we know kind of how that is built over time in development. So this is an interesting system to play with because we have all the parts specified. There's very little, variation between organisms within C. elegans, and we actually have good timing information for this. So we can play around with this small connectome, and we can actually build, in this case, what they're doing is they're building a simple stochastic generative model, which means they're going to build a model that allows us to see how the connectome is built over developmental time. So I'm going to read the abstract here. The architectures of biological neural networks result from the developmental processes shaped by genetically encoded rules, biophysical constraints, stochasticity, and learning. So this is just kind of the whole, the totality of everything that contributes to the development of a biological neural network. Understanding these processes is crucial for comprehending neural circuit structure and function. So we have to know kind of what factors play a role when to understand how this, the adult connectome that we see. The ability to reconstruct neural circuits and even entire nervous systems at the neuron and synapse level facilitates the study of the design principles of neural systems and their developmental plan. So here they use the developing connectome of C. elegans using statistical generative models based on simple biological features. So they use neuronal cell type, neuronal birth time, cell body distance, reciprocity, and synaptic pruning. So they use a number of variables to build this model, and not only build a model of its occurrence, but to build a generative model, which means they can generate different possibilities for this connectome and how it might be wired. And of course, like I said, the timing of the cells is deterministic. The sort of the organization of the connectome is deterministic more or less. But we have, a lot of plasticity in the larval worm, especially with respect to synapse, changes in synaptic connectivity. So synaptic pruning, synaptic maintenance, and these types of things. And so these are all things that were, are kind of not really well known, and they're actually maybe not even deterministic, and even in C. elegans. So our models accurately predict synapse existence, degree profiles of individual neurons, and statistics of small network motifs. And so this is where, we're talking about things we're talking about the connectome as a network with statistical properties. We can look at how, how many connections individual neurons have to other neurons, that we have different, patterns within the connectome, different patterns of connectivity, like, triangle motifs or some other, shape that gets represented through connectivity. So that's what they mean by motifs. So there are a lot of things we can predict from the network topology and things like that. Importantly, these models require a surprisingly small number of neuronal cell types, which we infer and characterize. We further show that to replicate the experimentally observed developmental path, multiple developmental epochs are necessary. Validation of our model's predictions of the synaptic connections using multiple reconstructions of adult worms suggests that our model identified the fundamental backbone of the connectivity graph. So they've basically said that they're successful with respect to predicting what this developmental connectome should look like, and the different variations of it. The accuracy of the generative statistical models we use here offers a general framework for studying how connectomes develop and the underlying principles of their design. So they present a novel family of generative developmental models which rely on a simple biological and physical set of features for the study of the architecture and the development of connectomes. And so they chose C. elegans because it's the only species for which multiple connectomes have been reconstructed at different developmental stages. And they cite reference 16, which we'll get to in a little bit. We show that models that we learned for one animal are highly accurate in predicting the detailed connectivity maps of held out parts of that connectome for a full map of another individual. So basically you can, because it's very predictable, you can take one part of one organism's connectome and it predicts some other organism's connectome. That's what they mean by that. But they do look at these, they do still look at the level of individual synapses, neuronal connectivity, and small network motifs. They characterize these developmental trajectories. So not only is it, very highly regular, but you can also predict these different developmental trajectories. As I said, the synaptic connections are highly variable given environmental constraints and individual experience of the worm or whatever. So you have these developmental trajectories that you can predict. But of course, since you have this framework that's highly regular, you can actually do this quite effectively. So we further characterize the developmental trajectories our models predict and their tight similarity to the observed ones. So they're actually very accurate in terms of predicting observed developmental trajectories. Our models show that the connectome of C. elegans can be constructed accurately using a surprisingly small set of design rules. While these models offer a general framework that can be extended to other neural systems, our findings already suggest that a surprisingly small number of parameters govern the design of neural circuits. So this is interesting that given this connectome, it's highly predictable in a lot of ways, but it also can give you these different developmental trajectories. And so, but you still have this, it's governed by a small number of parameters. It really isn't governed by that many parameters. We know that, for example, that not only do we have environmental variation, and that can have an effect on the larval connectome, but we also have defined mutants, of course, where we have these known effects of genetic background. And so, but even given all of that, we only have a few sort of parameters that need to be considered. So that's always good because in modeling, we want to have relatively few parameters to predict things. So they build their generative model here. They kind of go through this process for doing this. These models construct neural circuits using three basic operations They are carried out iteratively over discrete time steps. This is where neurons are born at specific times and locations, and we have that information available in the community. Synapses are formed independently of one another, with a probability that depends on the types of neurons they connect to and the distance between them. So we know that sort of the neuron birth times from the lineage tree. We know where they're going to be located. We have this information about synapses. And then, thus the probability of forming a synapse from neuron I, which is of type TK, to neuron J of type TL, in a given time bin is given by this equation, where STKTL is the baseline probability to create a synaptic connection for a neuron of type TK. So basically you have these pairs of neurons that are going to make some sort of synaptic connection, and there's a probability attached to that. There's a baseline probability, and then there's above chance. And so D is the distance between neurons. This is in space, so we know the positions of the cells, the location. We know the distance that they have to have. They have to have, of course, an axon that goes between them, but then there's synapses, and the question is there's what cells are most likely to synapse with other cells? Are they going to be close by, or are they going to be far apart, or what's the governing principle there? And then BT is a coefficient controlling the distance dependence, and its value is time dependent to reflect the impact of the elongation of the worm during development. So not only do you have to worry about this sort of axonal distance, but you have to worry about changes in the morphology as the worm grows. So this is where it's actually where the connectome grows over time as the worm grows, and you get this sort of elongation factor. Individual synapses are removed via pruning with probability S minus in a manner independent of these types of neurons involved. So then they want to study the connectome of 180 neurons. This is the nerve ring, which is the central part of the connectome. The detailed connectivity of the nerve ring has been reconstructed for several individual animals at different time points during development. Our model uses binarized maps of connectivity of the nerve ring of the adult worm. This is the basic form of the generative model. We have neuronal birth, synaptic formation, and synaptic pruning. And so we can see that we have this sort of, we're putting together these neurons as they're born. We have formation of synapses, and we have the loss of synapses. And so one of the points they make is a small number of inferred neuronal types is sufficient for building an even more accurate adult, where we don't really need to know a lot of the neuronal types. We can just kind of build the connectome. Generative models based on a small number of inferred types of neurons recapitulate neuronal and subnetwork features of the measured connectomes. Model inaccuracies reveal new design features of the adult connectome. So we can actually get, so the inaccuracy of our current model in predicting triplet connectivity patterns implies that synaptic connections are not independently formed. So this is where, we have these different, there's a reciprocity of synaptic connections in the experimental data, and it's much larger than projected by a standard Erdos-Renyi model, which is a standard network model of connectivity. So we have this sort of reciprocity that's expected, and when we have our model of the data from C. elegans, it exceeds that expectation. So that means that there's some reciprocity in the model in the C. elegans connectome that is above chance with respect to a standard model of connectivity. So that means that we have this sort of, maybe that there's some genetic aspect to, synaptic connectivity that, isn't like typical of a network model. And so, the inferred neuronal cell types of the model have clear biological interpretations. Multiple developmental epochs are necessary to recapitulate the measured developmental path. So this is given the accuracy of our generative model for the adult worm, we turn to study the development of the connectome using the reconstructions of the nerve ring for 8 different nematodes from this reference 16. Given that young larvae, there is only a single reconstruction available per age. To learn our models and validate them, we randomly split the total set of potential synapses of the adult worm into two halves. One half was used as the training data, and the other as the test data. This is a standard technique for all developmental stages. We then compared the accuracy of this expected value, which relies on a single set of parameters of the whole developmental process, with models that use 3 developmental epochs to predict the empirical connectome. And so basically you have this 1 versus 3 stage model. And so interestingly, the values of the probabilities of that the multi-epoch model assigns to individual synapses are higher than those of the single epoch model at early stages. Figure 6e, which shows the likelihood ratio of the models over different connectomes across development, demonstrates that the multi-epochs model is consistently better by a large margin in the early developmental stages. Thus, multiplicity of developmental epochs emerges a critical component for building the worm connectome. So basically, if you have more developmental epochs, the better the model. And this, of course, speaks to maybe what's going on in development, that nervous system development is divided into different parts, and that there are different sort of things that have to be in place before you can move on to the next epoch. So there's a lot in this paper, and I don't want to go through the whole thing. I just wanted to point out that this is a nice paper that really predicts or builds a model that predicts a lot of the experimental data. And so if we look at citation 16, you'll see that this is the Whitfleet paper from 2023. So this is Connectomes Across Development Reveal Principles of Brain Maturation. This is in Nature. This was a good data set. This is actually the data set we use for a lot of the synaptic stuff here. And so there's a lot of stuff in this paper. I'm not going to go through the whole thing, but this is a good new paper that came out on this developmental connectomes idea. So it looks like, I don't know if we have any questions about that. All right, well, if that's all for today, thanks for attending. All right. Thank you. Have a good week. Bye.